See, that's the difficulty with trying to have you go along with me, because I know that almost every other person has a problem, and then you get snagged on that problem and you can't continue. You're still wondering what we're on. So please just follow me and see if it makes some sense to you. All right, so I was at this point here where I was going to run the program xt by just saying xt hk. The other remarkable thing that it does is it adds extra data. If you have gaps in your data collection, it tries to fill them in for you. It's really a genius program. Okay, so it outputs, here you can see 3 possible space groups. Can you see it? Is it clear enough? It's kind of hard to see, I guess. Okay, P2 1 over n, however, is the favored one. It's the first one input. And if I want to look at the res file, it's going to be called hk minus a dot res. And then it'll be minus b minus c. So usually I would try the first one. Also, you can look at the expected R value over here. This is not actually the minimum expected R value, but these are all similar. So, you know, it's a possibility that it's not the first one, but it is. So to view it, you can go to XP. And after you run XP, you can say read and then give the file name. Or alternatively, you can also say XP space file name. Either way. The difference is read will not include the Q peaks. If you put it on the same line as XP, it will include the Q peaks. If you want to see the Q peaks, you could say reap. I sent you a list of commands, so you can look at what I sent too. That stands for read past end of file, reap. He always has cute reasons for naming things the way they are. So read is no Q's. And this is with Q's. Why? Because they appear after the end statement, right? So you're reading past the end of file. Okay. So I want to read, let's just read the file that's called HK minus, or underline A. Oops, I forgot the R, the D. Still, you don't see anything, because there's one more thing you have to say, which is fmol, F-M-O-L, which sets up the connectivities. So it looks like this. This atom numbering scheme is not my favorite. Everything is, of course, 4 characters, like everything that Shellix has. But it has all these extra zeros and everything. Now, if you want to see what it looks like, you could just say proj, short for project. And maybe that's not too clear, so you can rotate it. And at first glance, it looks like everything is there. You know, it's some kind of octahedral tin compound. I want to see the labels. You see tin is in the middle, and then it has 6 things around it. This group here, though, or the atom here, is a loner, and you can't really see it on this screen. I'm really sorry. It's just the resolution's not good enough. That's a water, anyway, it turns out. I thought it would show up clearly. Wonder why it's not better. I wonder if it's mismatch between the resolution of my computer and the resolution of the projector. I could try changing it. Should I? Hold on a sec here. We'll just try one thing. Wait, just do it this way. I mean, this is extreme, but I have a feeling it might work. Let's try it. It's clear, isn't it? It's better? Yeah. Good. Ooh. That's not much better, though. That's why I don't like this laptop. Okay. I'm just going to have to tell you then. What I see here is another command that's useful is mpln, which calculates the least squares plane of everything in the structure. And then when you say proj, you're looking down the normal to that plane, and it helps to spread everything out. So if I proj again, you see how more spread out it is? Can you see that? Now, I mentioned before that there's this one problem with XT, that it doesn't distinguish among oxygen, nitrogen, and carbon very well. And here you see no nitrogens being named at all, and it does have nitrogen in it. And the carbons are probably correct. But like this group out here at the end is actually nitrite, NO2, so that's got to be a nitrogen there. The other key to figuring this out is looking at thermal parameters. Yeah? So here, if we look at info, it lists, there's a lot of stuff here too that I should point out. So look at the peak heights, for example. The tin was by far the biggest peak. The oxygens have bigger peaks than the rest, but some of those oxygens could be nitrogen. Some of the carbons could be oxygen. You don't really know until you've worked with the structure for a while. But these are the assignments. The X, Y, and Z, and A tip has to do with the type of atom it is. Color is useful too. You can change that when you're doing graphics. ARAD is the size of the atom if you draw it. And it's roughly usually related to covalent radii, but here the only one that's changed is tin. BRAD is the covalent radius, and SRAD is the van der Waals radius. So you do have a nice table here. You don't have to go look it up somewhere else. Those are pretty accurate, I think. So there's a lot of information there. Okay, so I'm just going to take this and write it back as an INS file and refine it. This is a step where a lot of people get messed up when they're not used to this program, because you're going to be overwriting the res file, and sometimes you forget to write it as an INS file, and then you lose what you did. So what you have to do is you say file, and then give the file name. I'm just going to call it HK again and get rid of the underline A. So that's going to write INS file, hk.ins. And I want it copied not from hk.res, but from hk underline a.res. So I'll put that in here. And I could quit now, come back to that later. So the new file, hk.ins, is just set up. Yes, yeah, there's that. like so. It's pretty much the same header as you had before. It still contains like temp and size, which are things that were added. It's set up to do 10 cycles of least squares, calculate bond distances. List 6 is an option. That's a certain set of data that's being used. I usually just take that off, however. And Fmap to plan 20 means a difference map with 20 difference map peaks. And here's the atoms with their expected thermal parameters. Let's just do a refinement quickly and see what happens to those. HK. When I talk about convergence, I'm looking at these numbers here, the maximum shift and the maximum of a particular atom, and then maximum for the whole set. So this is actually converged as it is. The R value is quite good, 4% in some. But I haven't even added hydrogens yet or made things anisotropic. So this looks like it's going to come out really well, really promising, very good. The highest peak, 1.18, that's probably just because the tin isn't anisotropic yet. In fact, yeah. Or it could be a hydrogen. Could be a hydrogen. But let's look at the picture again. That looks the same. That isn't interesting. Let's look at info. Now, what I'm seeing here is some of these thermal parameters on the right, like for C00B, C00C, and so on, those are too small. The thermal parameters of 0.006, they're not in keeping with the rest of the structure. So even though they're called carbon here, I'm wondering if they're really carbon. They might be nitrogen or they might be oxygen. So let's try a quickie numbering scheme so it's easier to work with this. And the way I would do it is just with pick here. So what this does is it blinks for the atom that it's waiting for you to rename. So I'm just going to go with the fact that it's carbon and call it C1. These are all carbons. I'm not worrying about doing it in order because I may change the atom type later and then I'll just have to do it again anyway. So. Then there's a sort feature. You don't want to use the same atom name twice because that'll cause the refinement to crash. It doesn't like that. So you can just say sort, which is sort of a partial sort. It does sort stuff, but it has oxygen 7, C7, and I'd rather have oxygens all together in a group. So to do that, you can say sort SN1, oops, $O, $C. I don't have any nitrogens left here. Okay, so it looks like that. Now again, C19 through 22, the thermal parameters are too small. Can we tell anything from this structure? Those are down at the end there, for starters. See where C20 is and C22? I suspect those are nitrogens, not carbons. Another key would be to look at bond distances and bond angles and that sort of thing. And the other ones that are too small are C19 and C21. So what if those are nitrogens? They might be. So we could go through and do pick again, or we can just name them. You can say name C19 and 1, name C20 and 2, name C21 and 3, name C22 and 4. And the program is going to automatically change the SFAC for you when you do this, so you don't need to worry about the SFAC number. Then you might say, well, C1 and C8, are those really carbons bonded to the tin? Yeah, you can have that. How will we know if those are carbons? Look for hydrogens, see if it's a methyl group. You see which ones I'm talking about? Yeah, that one and that one. You may be surprised that that could actually be a methyl group. And this nitrogen here, I actually had to look up what that was on the CSD. So it's, do I have it in my pocket still? That particular ligand, if it's correct, is what is called a hydroxamic acid. So it will have been deprotonated, and so each ligand will have a -2 charge, a -1 charge, and then the methyls contribute a -1, so it's tin 4, which makes sense. Okay, so let's try refining it like that. So again, I'm going to say file HK, and now that is the correct res file, so I just hit enter, quit, and XL HK. Okay, our value did go down a little bit, but again, we don't have hydrogens. Still, we don't have anisotropic things. And how about thermal parameters? Did those get corrected when we changed them to nitrogen? Let's see. This is an easy way to see them by just saying info. Yeah, they look better because they're more in keeping with the rest of the atoms in the structure. So I believe they are nitrogens, in fact. And everything else looks reasonable enough. So let's try making them anisotropic. So I'm going to edit the res file now. Just edit it in Notepad. I want to say anis, and that'll apply to everything. And maybe increase the plan a little bit, because who knows how many hydrogens there might be. See what they look like. Maybe 30. And then save as ints. Yes. And refine again. Now you don't have to keep typing this. This is a nice thing about the command prompt. So you can just use the up arrow to use an old command. So I'm just going to use the up arrow to get back to one that I used before. All right, the R value went down a lot, but making things anisotropic usually does do that. Now let's have a look at the difference map. I want to do REAP this time. Oh, let's do M-plane. Now there's a bunch of stuff around the tin. You expect that. But I think you can see the methyl groups pretty clearly now. Those carbons that were by themselves definitely are methyl. You know, there's a bunch of stuff there that looks like there are hydrogens around those. Neglect those. I think the rest of it's going to come out just by the automatic addition of hydrogens. So you don't need to add them one by one, but just to verify that those are methyl groups. So I'm going to kill the Qs and just say H add, hydrogen add. Now let's see what it looks like. So all of those dotted lines are hydrogens that have been added. There's 4 methyl groups. Each of those carbons has 3 hydrogens. The O5, which is actually a water, those hydrogens aren't going to be added geometrically because you never know which way they should go. So those do have to be looked for in a difference map. So let's refine it just like this and then look for the hydrogens on the water and see if they show up. Okay, so I'm going to do an escape and say File, HK, okay, and then quit, and then Excel again. Again, our value is still coming down, getting lower and lower. And go back to XP, HK. I'm not sure what that is it's complaining about. But now you can say bang, which is short for bonds and angles. Bang. 07, I think that was the water. No, it wasn't. Which one was the water? It was that one out there. 05. Okay, bang, 05. Those look like hydrogens to me. You see, the OH distance is about 0.9. The angle is 103.7. That's kind of remarkable in a way that you see the hydrogens, but you see them when the R value is low, even though there is a heavy atom present. So I could just name them, name Q4, H5A. Oh, that already exists. Name Q4, H5B. That also exists. All right, let's just call it D. Okay, that doesn't exist. And Q10, H5E. Now later, I'm going to renumber this anyway. But just want to have unique atom labels at this point. And all the rest of the Qs we could just kill. So what's it look like now? It looks like this. Now that O5 there's a whole lot of oxygens here, so it's probably hydrogen bonded to something. So a nice thing about this program is you can actually find hydrogen bonding pretty fast, or you can do the H-tab feature in Excel, and it will also find them. But this one has a very interesting way of attaching itself to the complex. I want to show you that. So remember, the distance between a hydrogen and oxygen and hydrogen bonds usually around 1.7 or 8 or something like that. So I can say NV say 1.8 H5E. And here is a listing of, now these aren't all bonds, but they're non-covalent distances. You see that H5E is kind of close to 08, 2.29, but these 4 numbers here that precede that, 1545, are telling you by this ORTEP code that it's in a different general position. It's not just connected as I have it now. So I need to shift it to make it connect in the picture, which is a little tricky. I want to say move the water, not the other molecule, but you could do it either way. So what should I do here? Oh, the way these codes work, I should tell you. Okay. So if you say sim here, it'll list the symmetry positions. Can you see those? Yeah, you can see those. So 1555 refers to where you are now, X, Y, Z. 2555 is the inverted position, minus X, minus Y, minus Z. And so on. 3555 is as it's stated there. So what if it's not 555, but 545? That means that you take 1 away, translate by -1 in the Y direction. Yeah, exactly. So it's just a unit translation. If it says, 1575, then you would translate by 2 along that direction in the positive direction. So lower than 5 is negative, higher than 5 is positive. So these are the the codes that were developed by Ortep a long, long time ago. Yeah, you have to kind of get used to it, but it isn't that hard. I mean, I can explain it to you easily. So what I want to do now is shift that water molecule so that it's closer to the tin complex. So another way to do it is to say NV, it's 08 is the one that it's close to. So I can NV 1.8, 08. And H5E it's the same symmetry operation. So how do I move it? I say SGen, which stands for symmetry generate. Everything has a meaning. With a minus sign. Minus meaning don't make a copy of it, just shift it. And then I'll say 1565 H5E. And then, because I think it's hydrogen bonded to 08, I can link it. I can say link 08 H5E. And then when I make the projection, oh, I needed to move the whole molecule. Duh. Yeah, we can't just do that one. So, let's just say bang 05. So I'm going to shift these other two atoms as well. So SGen minus 1565 05 H5D. So this is going to shift the whole water. And now, that's the wrong link. So I don't want this to be connected. That was wrong. So what I think you can kind of see that there's a position that makes it possible for this water to bond to both 08 and 09 here. It's kind of cute. So I can say link H5E 08. That's one, and then the other one, H5D. It's kind of neat. And if you want to see it in 3D, you can say IS2, for example, and do the same thing. And it looks pretty neat. Okay, so can I just take a few more minutes here? Okay, so we can refine this, and it comes to a really low R value. But to finish this, I would want to rename it and sort the atoms in a sensible way. The other thing you want to do is make sure that the unit statement has the correct numbers of the different kinds of atoms. You want to make sure that you've included hydrogen bonding, that the highest peak is less than 1, which it is, and you want to update the weight. So the weight right now is at the end. So this is one way to do it. A lot of the programs that you may use will do it automatically for you. Oops, it's not there. It's in the res file. Right here. So I can just take out the FMAP2 plan 30, put in ACTA. I can also put in HTAB. HTAB will compute the hydrogen bonds and set it up for you. So have a look at the end of the res file. It's set up the hydrogen bonding already. The first one, the H-tab C18 to 09, I don't want to include that because that's a CHO distance, pretty unimportant. But these two are important, so I can cut and paste those and put them at the top. Okay, so a little more fiddling in. This is done now. I was confused about the ligand because it looked like a really strange thing to me. So I went to the CSD to see if it had been reported before. So let's see if this works at this resolution. Doesn't even show up down here. Hold on a sec. Okay. You see how these letters look too small? It's kind of crazy. But so I wanted to just draw the ligand and see if I could find structures that had that. And looking at the bond distances and angles, it looked like it was delocalized, that there were lots of resonance structures. So it wasn't really clear where double bonds were and where single bonds were. So I just drew it. So you can start out with, say, a phenyl ring, like that. And then it goes to a carbon. Just that. And then it goes to a nitrogen. Then it goes to another oxygen, to an oxygen. And this goes to oxygen. And then it goes to tin. But let's leave off the tin, because it could be some other metal. I'll leave off the NO2 group also, but this is the part that was confusing to me. I suspected that this was a double bond because it was 1.27 angstroms long, so that's, again, I'm sure it's delocalized, so these other ones aren't necessarily only just single bonds. Oh, and there also is one more carbon here, which is actually a methyl group. And if I want that to be a methyl group, you can go to groups, pick CH only, click on methyl, and just change that to methyl. So that's roughly what the ligand looked like, except that it had NO2 in this para position here. And then there's a tin that's bonded to this oxygen and this oxygen. Okay, so I just defined the structure at this point. I just want to see if anybody else has published anything like this, what it is. Not being an organic chemist, it looked a little weird to me. So I just said search and start search. And so, lo and behold, I mean, this is sort of similar here, this one, the first one that's in there, the Bohe one. If I want to see what it looks like in 3D, I can do this. You see, it does look kind of the same, right? What did they call it? If I go to alt text, they're calling a hydroxylamine. Okay, similar. Let's see what other ones there are. There's a Bohe 01 here. That's just a redetermination, probably of the same structure by somebody else. Here's this one, so on. So it's definitely a ligand that's been used before, or a compound. So there it is the acid. What do they call it? They call it 3-bromo N-hydroxy and methylbenzamine. All right. If you want to just scroll through this, you can see, for example, at the top, the reference, you can see the latest ones. So it's got different names. Here's one that's called hydroxamido, so that's more like what I'm seeing here. Go back to diagram. There's a complex with something similar. And again, you want to see it in 3D, you could rotate like that. Notice that, no, they don't have it anymore. They used to have stereo here, but they don't have it anymore. You can do picking mode here and pick distances and actually check the distances and see if they correspond to what you're getting. So that's short, so that's the main double bond, but some of these others are kind of short too. So anyway, I was glad to see that it did make some sense and it's been published before. So that's one use of the CSD, is just to see if what you have is good. Or you could also see if it's just a duplication of something that's already known. The fastest way to check that, though, is to go to the bond distances, the unit cell. So if you do build queries and click on unit cell, you could input your lattice, your cell parameters within a certain tolerance, and just if it's exactly the same structure and been published before, it'll pop up. I did that, it hasn't been published before. But that's also something you can do quickly, and you can find out if you actually have something new. So there are many, many things you can do with the CSD. If you have it, then explore it and find out what things are useful for you. And if you have any questions about these searches, I'd be happy to answer them. Okay, so the structure pretty much is done, except for doing the SIF. And so I want to spend some time on doing SIFs, probably next time. Okay? So we'll do that. Any questions about what we've done so far? I'm sorry that it doesn't show up better. I'm very disappointed with this computer. Yeah. So that's just not very good resolution. Okay, I think that's enough for today. Let's call it a morning.